Hello everyone, welcome back to the course Expansive Soil. This will be the lecture number 21st, and in module 7 it will be about the treatment of expansive soil, and this we will discuss about the chemical methods. In the last class I explained you about the various lime treatment methods and how the soil strength gains and what are the different reactions takes place during a lime method. We discussed all those things in the last class. Today I will continue with this same topic and I will be discussing about the other methods of chemical stabilization. By adding cement to the soil, we can gain a large amount of strength, and this is one of the most popular method which has been used around the world. So this is a very common method, and this method can encounter a problem when there is a organic matter or sulfate present in the soil, and when we add cement to the soil, then the cement will be hardened faster. So if we are not compacting the soil immediately, then we have to add some of the retarding agent. If there is a delay in the compaction, then we need to add some retarding agent such that the soil will not get solidified because of the cement. Sometimes we can replace the cement by fly ash, particularly when we use the soil cement mixture as a filler material. In that case, we can replace the cement by fly ash. And also the calcium chloride can be used if the organic matter is present in the soil. In the cement addition, the hydration reaction is responsible for imparting strength to the soil, and since this hydration reaction is independent of soil type, this cement stabilization technique can be used for wide range of soil. But here we need to remember that if the liquid limit is higher than 40, in that case the treatment will be more beneficial if we use lime instead of cement. Therefore, this method mostly used for the soil which has a liquid limit less than 40. So when we add cement to a soil, then the cement will react with the water which is present in the soil, and due to this reaction between the cement and water, it will produce calcium silicate and aluminate hydrates, and this calcium silicate and aluminate hydrates will bind the soil particles together, and therefore the particle size will increase and the bonding between the particles will increase, and as a result the soil strength will increase. Due to this hydration reaction, the slaked lime, that is calcium hydroxide, gets released, and this will react with the soil mineral, and since the hydration is independent of the soil type, cement can be added to wide range of soil. And as I told you earlier, for a highly plastic clay with a liquid limit higher than 40, the treatment with lime will be advantageous. These are the general procedure which we need to adopt for a soil cement stabilization process. In the first step, the excavation of the soil will be carried out, and the larger particles can be broken into small particles such that the mixing can be uniform. Once the excavation or the pulverization steps complete, then the cement will be added to the soil along with water. Immediately after adding the cement to the soil, the mixing will be performed, and after the mixing, the soil will be compacted using a compactor, and once the compaction is finished, then the soil will be allowed for curing. And if there is a delay in the compaction after mixing the soil, in that case we need to add some retarding agent such that the soil will not get hardened because of this cementing process, or that will delay the pozzolanic reaction, and because of that the hardening of the soil will not take place before the compaction. If we are using a plastic soil, then in that case the workability will be less. So in order to increase the workability, we need to add 1 to 3% of the lime to the soil. So addition of this 1 to 3% of the lime will increase the workability of a plastic soil such that the mixing and compacting can be done without any problem. These are the different factors which can affect the cement stabilization process. The cement content, generally with increase in the cement content, the strength of the soil will increase. The method of compaction. The next is the time elapsed between mixing and compaction. If there is a time gap between the mixing and compaction, Because of this pozzolanic reaction, the soil will get hardened because the cement will start to settle in. So, therefore, the soil cement mixture will start to harden, and if there is a large gap is there between mixing and compaction, then the compaction process cannot be carried out with a good amount of compaction. Therefore, the strength gain cannot be achieved what it should be. Next will be the duration of curing. Duration of curing means once the soil has been compacted, we have to allow the soil for curing. During this curing process, the soil will gain some strength. So, therefore, if the duration of the curing is less, the gain in the strength will be less. Next is the temperature and humidity. Since the pozzolanic reaction depends on the temperature and humidity, generally the strength gain will be higher if the temperature is bit higher. We need to add a different amount of cement to different type of soil. Say for example, for a gravel soil, 5 to 10% of cement is required by weight. For a sandy soil, we need to add 7 to 12% of the cement. For a silty soil, it will be 12 to 15%, and for a clay soil, it should be around 12 to 20%. So, these are the different amount of cement which is generally required for different type of soil. Now, in this table, we could see the effect of cement content on the strength of different kind of soils. Here you can see for a silty clay, when we add 7% of the cement, it will exhibit a higher value of compressive strength. In comparison to gravel, the same 7% of the cement content gives a less amount of the compressive strength. However, with the increase in the cement content, the compressive strength of all the soils keep on increasing. However, for silty clay, the increase in the strength will be less in comparison to gravel. We could see over here at 13% of cement content, the gravel will give a higher amount of compressive strength, whereas the clay will give the least amount of compressive strength. And similarly, the clean sand will also give a large amount of compressive strength in comparison to the fine grained soil. Therefore, the cement content will play an important role in defining the compressive strength or achieving the compressive strength of different soil. So, generally the strength of clay soil will increases less due to the addition of the cement in comparison to the gravel soil or coarse grained soil. So, for a coarse grained soil, the increase in the strength will be quite large in comparison to the fine grained soil, for which the increase in the strength due to the addition of the cement will be quite less. So, these are the different engineering benefits of cement. So, major benefits of adding cement to the soil is its increase in the strength and the stiffness. Then better volume stability, that means it will reduce the swelling and shrinkage tendency of the soil, increases its durability. If we look into the density, then the maximum dry density of sand and highly plastic clay will increase. However, this for silt it will decrease. Similarly, the optimum moisture content will not change significantly due to the addition of cement. If we look into the plasticity behavior, then addition of the cement will reduce the plasticity index of the soil, and therefore it will reduce the plasticity nature of the soil. Strength gain is the most important factor, and we could see here with increase in the cement content, the compressive strength of the soil will increase. Another factor which is most required for an expansive soil is swelling shrinkage control or swelling shrinkage stability or the volume stability. Even addition of a small amount of cement can decrease the swelling shrinkage of a soil significantly. Therefore, the cement can be used to control the swelling or shrinkage of the soil quite effectively. Next comes the fly ash. Fly ash is another product which can be used along with other materials. Generally, fly ash is not used alone for a soil improvement. Fly ash are generally used along with the lime or cement. Fly ash is a solid waste product which will be created by the combustion of the coal, and then during this process it will be carried out by the flue gases, and then it will be extracted by an electrostatic precipitator, and from that electrostatic precipitators it will be collected. If the ash is collected from the bottom of the furnace, then it will be known as the bottom ash, and generally this bottom ash are coarser than the fly ash, and bottom ash is mostly used for structural fill and in road construction, and also they do not exhibit more pozzolanic reaction, and fly ash is used as a replacement of cement because of this their pozzolanic behavior. When we take fly ash can be divided into two way, class F and class C, as far as ASTM C618. This classification of the fly ash depends on their chemical composition. Class F fly ash produced from the bituminous core, whereas class C fly ash produced from subbituminous coal. Class F fly ash do not show any kind of pozzolanic behavior, whereas class C fly ash generally shows the pozzolanic behavior. Since the class F fly ash do not show any pozzolanic behavior, it needs addition of lime or cement for the treatment of soil or for soil stabilization process. The principal chemical composition of a fly ash are the silica, alumina, ferric oxide and calcium oxide, and there are different factors which can control the physical, chemical and engineering properties of fly ash. Those are coal type and purity, as I told you before, that whether it is produced from bituminous coal or subbituminous coal. So, the fly ash can be differ as F or C. So, therefore, coal type and purity can control the physical, chemical and engineering behavior, the degree of pulverization, the boiler type and the operation. So, these are the different factors which can control the physical, chemical and engineering properties of the fly ash. For a cohesionless soil with very low plasticity, generally with a plasticity index less than 10, cement will be more beneficial than lime, either alone or in combined with the fly ash. For more cohesive soil, cement can be added with lime and fly ash for the soil stabilization. So, when we take fly ash, generally fly ash has to be added with cement or lime for a soil stabilization process. If we look into the different properties which we can get from adding fly ash cement or fly ash lime to the soil, we could see that fly ash cement in comparison to fly ash lime will give a higher density at a approximately identical water content or little bit less water content. So, by adding cement to the fly ash, we can achieve a higher density in comparison to the addition of the lime to the fly ash. Similarly, if we compare with the UCS value with the fly ash content, we can see generally we can get a higher value of strength when we add cement to the fly ash in comparison to the lime. Similarly, when we compare with the water content with the UCS value, we can see here by adding the fly ash, we can achieve a higher value of UCS at any water content in comparison to lime. So, here we can conclude that addition of the cement will be more beneficial in terms of strength gain, achieving higher density in comparison to lime. So, therefore, cement treated fly ash is more preferred in comparison to the lime. So, these are the different effects due to the addition of the lime and cement on the behavior of fly ash. The next comes the bitumen and tar. Generally, bitumen and tar can also be used for soil stabilization process, and bitumen is a product obtained after the processing of the residue that remains after the distillation or evaporation of the crude petroleum, whereas the tar is produced by the destructive distillation of the coal or other carbonaceous material. When we use the bitumen, it is generally used either in the form of emulsion or as a hot bitumen, and generally this bituminous stabilization is used for waterproofing the soil or to reduce the water absorption and add cohesion to the soil. When particularly used for clay soil, generally the strength gain for the bituminous stabilization is not that much, but in that case we can get a large amount of waterproofing. So, we need to remember for clay soil generally this is used for waterproofing, as the strength gain is less. Bitumen stabilization can be used for many kind of soil. So, for example, sandy gravel, sands, clay sand and silty sand. However, if we are using a plastic clay, then in that case we need a higher amount of bitumen to be added with the soil. These are the general steps or different procedure for a bitumen stabilization soil. First, the soil will be pulverized by excavating the soil and crushing the large particles. Then we need to add water to the soil for proper mixing. Once the mixing is done, then we have to add bitumen to the soil and the mixing will be carried out. Then we have to do the aeration to proper volatile content for compaction. Then we need to do the compaction to the soil. Once the compaction is completed, then aeration and curing will be performed. So, these are the different steps which we need to follow for a soil stabilization using bitumen and tar. So, these are the different engineering characteristics of bitumen mixed soil or bitumen stabilized soil. In this graph, the tar content has been plotted along with the maximum dry density for different viscous tar. So, here we can see with increase in the viscosity, the maximum dry density for any given tar content will be more. That means, if a soil is mixed with a highly viscous tar, then the density which can be achieved will be higher if it is mixed with a tar of higher viscosity. So, here you can see this is a highly viscous tar, and for the same content we are getting a higher value of dry density in comparison to a low viscous tar. If we compare with the optimum moisture content, almost those will be identical, but at larger water content there will be a difference over here, and the OMC for a highly viscous tar will be more in comparison to the less viscous tar. If we see the water absorption of tar treated soil, then we could see by adding a tar to the soil, the water absorption capacity of the soil is decreasing. Since the tar will coat the soil with an impermeable layer, the water absorption capacity of the tar treated soil will be decreased. We could see here, even after different days of soaking in water, the water absorption capacity of different soil treated with different amount of tar will be different. Higher is the tar content, lower will be the water absorption capacity for any days of soaking. Similarly, if we compare with the unconfined compressive strength, we could see with increase in the tar content, the unconfined compressive strength of the soil will keep on increasing, but after reaching a certain value, then it will start to decrease. Similar kind of behavior can be achieved irrespective of the days of soaking. However, if we soak the soil for a large amount of days, then the achieved unconfined compressive strength of the soil will decrease. So, here you could see that at 1 day of soaking the strength is quite large, and after 6 days of soaking the unconfined compressive strength of the soil will decrease. As after 6 days of soaking more water will ingress into the soil, the unconfined compressive strength of the soil will decrease. For a fine grained soil, the increase in the bitumen content do not increase the strength of the soil, but with the addition of the bitumen content, it will give some waterproofing characteristics to the soil. Therefore, the fine grained soil will absorb less amount of moisture by treating with the bitumen. Generally, all the process which I have discussed so far, that is the cement stabilization, the lime stabilization, the Flyash stabilization or bitumen or tar stabilization, are performed at a shallow depth. But when we need to increase the strength up to a larger depth, then we can go with the grouting method. So grouting can be defined as the injection of fluidized materials into the voids of the ground or space between the ground and adjacent structure, and generally it can either through boreholes or it can be injected under pressure to change the physical characteristics of the formation. So when we inject some grouting material to the soil, it will seal the voids or cracks or fissures which are present along the soil, and because of this sealing of these voids, it will increase the strength and also it will reduce the permeability of the soil. Therefore, the main objective of a grouting process is to produce a stronger, denser and less permeable soil. So, going by the procedure, grouting can be divided into two ways. One is the compaction grouting and second one is the permeation grouting. In the compaction grouting, the grout will be injected into a soil through its interconnected voids or pore space. So, in this space, the injection of thick consistency soil cement grout under pressure will be injected into the soil mass, and they will then consolidate and thereby densifying the surrounding soil in place. So, here we could see in this compaction grouting process, the grouting material, which are generally a thick consistency soil cement mixture generally are used. In this, the grout material will be injected with a large amount of pressure, and when we inject this grout material, then it will get solidified and then it will densify the surrounding soil, and therefore the strength of the surrounding soil will increase. This is generally carried out for densification of the foundation of the soil and raising and relieving the structures and foundation elements. Here we need to remember that in the compaction grouting, a very thick consistency grouting material will be injected to the soil with a large amount of pressure, and then once it gets injected, then it will get solidified and thereby it will compact or compress the soil which are present surrounding that area, and therefore it will increase the strength of the soil. In permeation grouting, the grouting will be injected to a pervious soil, and in this case the consistency of the grouting material is not that much, and in this case the soil or the grouting material will permeate into the soil through the interconnected voids. So, therefore, in permeation grouting, the grout is injected into a porous medium without disturbing its original structure. There are different types of grouting are available. Penetration grouting is defined as the process of filling joints or fractures in rock or pore spaces in soil with a grout without disturbing the formation. It is also referred to the replacement. It can be intrusion grouting or a permeation grouting. So, this is a permeation grouting and this is an intrusion grouting. So, here the grouting material will be injected. Over here we can see this is grouting material. The next one will be the compaction grouting. In the compaction grouting, a very stiff mortar will be injected to the loose soil, forming a grout ball here, which will displace the soil surrounding here and densifying the surrounding soil without penetrating into the soil spores. So, this is the displacement grouting. Next will be the jet grouting. In the jet grouting, a high speed water jet will be performed here, and this water jet will rotate in this direction, and this will then cut or made a cut like this. Then this will be filled with the grouting material. So, jet grouting is a technique where high speed water jets emanating from a drill bit cut into alluvial soil. As a drill bit is withdrawn, then the grout is pumped through a horizontal nozzles and mix with or displace the soil. And based on the material used, the grouting can be a chemical grouting or a slurry grouting. Chemical grouting means different type of salt solutions can be used. In the slurry grouting, a thick slurry of grout material, mostly cement, can be used. So, in this method, thick slurry of grout material is injected into the soil. This grout cannot be injected into the soil finer than the medium to coarse sand. So, therefore, for a fine soil we need to use the chemical grouting, and for coarse grained soil we need to use slurry grouting. The grout materials can be differentiated into three different materials like suspension grouting. In this suspension grouting, small particles of solids are distributed in a liquid dispersion medium. So, example is cement and clay in water. In emulsion grouting material, a two-phase system containing minute colloidal particles of liquid in a dispersed phase used as a grout material. So, example is a bitumen in water. In solution grouting, liquid homogeneous molecular mixture of two or more substances can be used as a grout material. So, example is sodium silicate, organic resin. So, depending on the soil and the uses, we can select any of these three grouting material. So, here we can see what type of grout material we have to use depends on the particle size. Generally, finer is the particle size, we have to go with the chemical solution. Since the chemical solutions are finer, or it is a like a liquid, so it can easily permeate through the void space, as the permeability of this soil will be less. So, therefore, we have to use the chemical solution. If the soil is a coarse grained soil like a gravel or sand, then we can go with the regular cement slurry mixture, or we can go with the water glass solution. And if it is like a cobble, then we use the mortar as the grout material. There is a design criteria for a selection of the grout. Generally, the volume of the grout to be injected depends on the porosity of the soil, grout spacing and depth of treatment. And the groutability of soil with particular grouting can be evaluated based on this N value. So, this N value is defined as the D15 of the soil divided by D65 of the grout material. If this value is greater than 24, then the grouting will be feasible. If it will be less than 11, then the grouting will not be feasible. This can also be defined using another term, that is with the NC value. So, here NC is defined as the D10 of the soil divided by the D95 of the grout material. And in this case, the grouting will be feasible if NC is greater than 11, and if it is not feasible if NC is less than 6. So, depending on the N values or NC value, we need to determine whether the particular grout material can be feasible for a grouting or not. Next is the chemical grouting. Generally, the other groutings are very thick in nature. So, therefore, those grouting material cannot be used for a fine grained soil. So, in chemical grouting, it will be relatively low viscous, such that it can be injected into a soil without any pressure, and due to their low viscosity, chemical grouting can be penetrated into fine soil, and the penetrability of the chemical grouting is a function of the solution viscosity, whereas the penetrability of the particulate grout is a function of the particle size. And chemical grouting can be used for any fine grained soil, and in this case we do not need any pressure for injecting the grout material. Then the question comes, what kind of grout material we need to select. The selection of the grout material should be in such that the grout material should be stable, should be less viscous and have proper settling time, and also it should not be toxic, it should not be corrosive, and it should not be exploding in nature. And depending on the permeability of the soil, also we can see whether the soil can be groutable or not. If the permeability of the soil is 10 to the minus 6 centimeter per second or less, then the soil can be termed as ungroutable. If it is between 10 to the minus 5 to 10 to the minus 6, it will be termed as groutable with difficulty. 10 to the minus 3 to 10 to the minus 5, it will be termed as groutable with low viscous grout. 10 to the minus 1 or more, groutable with suspended solid grout. So, depending on the permeability of the soil, we can choose what kind of grout material we need to take, or whether it can be groutable, If it is a groutable, then what kind of grouting or what should be the viscosity or what kind of grouting material we can use. Again, depending on the particle size, the various grout materials can be used are like, if it is a coarse sand, then cement slurry can be used as a grout material. If it is like fine sand, then bentonite can be used as a grout material. If it is a very clay soil, then compressed air can be used or acrylamides can be used. So, depending on the particle size, the different grout materials can be selected. So, these are the different references which has been used for preparing this lecture, and thank you very much.